Okay, how's everybody doing? Is there any audio coming from the speakers up there? No. That's on. So there's something coming, it's just not loud enough. How about now? And now? And now. Okay, that's too loud. Okay. So, a couple of administrative announcements and maybe a demonstration if the internet is working today in this room. Seems not right now, maybe later. The submission server is online in beta form, so for most of you, that means you can, well, probably most of you haven't even looked at the assignment yet, but for those of you who have been working on the assignment, you can now test your implementations and see if they make it through the submission server's tests. What you can't test yet is your tests. So you can do part 1 of the assignment and see how that does. Part 2 is still not up. That's the beta part of it. And be aware that it's not recording your marks at this point. So if you test now, be sure to actually really submit closer to the deadline. Okay. Has anybody tried it yet? Yeah. And it works? Gave you 100%? Yeah. 40 on 40? Good. Yeah, I don't know, because I only have 2 implementations. The one I did, which works perfectly, and the skeleton code, which gets 0. So hopefully some of you will see something in between those two values. All right. Any questions about anything before we jump into new material? So some of you have been using the forums. That's good. One thing I will tell you is a lot of people come to see me, let's say during my office hours or otherwise, and ask the standard question is, I'm using IDE X, and how do I make it do what it's supposed to do with the assignment? My standard answer is, I don't know. I don't use IDE X. But there's lots of other students who probably do. So whether X is Dr. Java or JCreator or NetBeans or Eclipse, there's probably lots of other students who are using that IDE. A few of those students will know how to make it do what you want it to do, whether that's take command line arguments or read from standard in or even just how to terminate standard in. Just ask the question on the student forum. That way you can ask it once. Everybody will get to see the answer. Okay, so that's my recommendation there. And this is where we start the real part of the course, which is learning about implementations of data structures, how they work, how efficient they are, and why they're efficient. So we'll start with, let's say, the simplest data structure implementation that we have available to us. And in the Java collections framework, let's say the most common thing that you use, the most likely thing you are to use, is this ArrayList class. So remember, an array list implements the list interface. So that means it has to implement these operations. Get the element at index I. You have to be able to set the element at index I to X. You have to be able to add an element at index I, so add the element X at position I, and you should be able to remove the ith index. Okay? And an array list implements this thing as an array. Okay? So there are two variables, two things that it needs to do this. So in the textbook, this thing is called an array stack, and we will talk a little bit about why that name is chosen in the textbook instead of array list. And so that's the implementation we're going to look at. We're not going to look at the Java Collections Framework array list implementation because it has a bunch of cruft that doesn't actually, it's more about Java than anything else. The array stack implementation sort of gets the main ideas across without any extra clutter. So there's two things. We want to implement a list using an array. So the first thing we need is an array. And that thing is called A. So an array, remember, is a block of memory that's able to store a bunch of values indexed by positions indexed 0 through a.length minus 1. Okay, so an array has a length, which tells you the indices you're allowed to use on it. It has a type, the type of values that it can store. So whatever type of values you're trying to store in a list, in your list, that's what you put in there. And in addition to the array, it stores one more variable, n, which is the number of elements in the list. Okay? So picture looks like this. You have this array. There's some elements stored in it, starting at position 0, all the way up to position what? What's the last thing in the list? Yeah. And not length minus 1, n minus 1. So in general, n and the length of the array are not the same. We know that there has to be some relationship to them because we can't have n being bigger than the length because then we would be trying to stuff too many elements into an array that can't hold them. So in general, at all times, we will have n is less than or equal to the length of A. We can't have it the other way around. We can't have it bigger because then we wouldn't have enough room to store the n elements that are supposed to be in the list. Okay? So indeed, there's the two main pieces of data in this class. The array that we're storing things in, they store elements of some generic type t and this integer n. Okay. So far we know enough to implement these operations. So get I is supposed to return the ith element in the list. How is that implemented? If this is our representation of the list, then how would we implement the get operation? Yep.
Just return the ith element in the array?
Yeah, we just return the ith element in A. So get I just becomes return A at I. It's just a one-liner. Okay. How about if we want to set the ith value in the list equal to x? What do we do then? Yeah. Yeah. A at I is equal to x. It's another one-liner. So there's basically the code for those two things. We can check to see if it's actually any more complicated than that. So there's the get method. Indeed, all it does is return a at I. The only thing it does is try and behave a little bit nicely and catch programming errors. It won't do that if I is less than 0. That doesn't make sense to be accessing an element with a negative index. And it won't do that if I is bigger than n minus 1, because then you're trying to access things that are not in the list. Okay. It might be in the array, but they're not in the list. So if you try and do either of those two things, then you get an out-of-bounds exception that occurs. But otherwise, you just get the value at the ith position in the array. Okay? And set is a little more complicated than it looks a little more complicated than it is. If you read the documentation for set in the list interface, you'll see that it's supposed to set the ith element of the list equal to x, but it's also supposed to return a value, and the value that it's supposed to return is the old value that used to be at that position in the list. So set is basically, the key thing is we're setting a at I equal to x, but before we do that, we save the old value in this variable y, we set a at I equal to x, and then we return y. Okay. So those two things work exactly like you would expect. All right. Looks easy enough. How about this add operation? So what's this add operation supposed to do? If I add an element to the list at position I, it is supposed to, well, it's like setting that element to that value, to this new thing that I'm adding, x. But everything after position I and position I should be shifted. So it looks something like this. If I say add I x, and this is I, then all of these things are supposed to move over by 1, and this new thing is supposed to go here. Okay. So can we do that here? So what does that look like? What does the implementation of that look like? What's the first thing you have to do? Yeah. A, B, C, D, E, F, G, H. Okay, so I am trying to put x at this position I here. And so what you're saying that I should store E before I do that. Okay, so I can store E, I can save E. Then what do I have to do? Yeah.
We have to move E, F, G, and H over by 1.
So we have to move E, F, G, and H over by 1. So how do we do that? Yeah.
Create a for n element and make n minus 1 equal to that element, and then go to n minus 1, make n minus 2 equal to that. So you start from the end of the array and just move back until you get to where you're trying to get to.
Okay. So we start from the end of the array here, position n minus 1, and we move that to position n. That means this thing is free for us to overwrite now. So that puts the h here. Now we go back one step to position n minus 2, and we move that to position n minus 1. So h gets overwritten with g. And we do it again. Now g gets overwritten with f. Now we do it again. F gets overwritten with E. Now we have two copies of E here, and we are free to overwrite the first one, the X. Okay. So super common beginner mistake. would be to execute this loop and not starting at the end, but starting from here, which would do what? It would copy E across all of these values here. So you have to start from the end to make this work. Otherwise, if you started at E, then you would copy E to here, and then you would copy E to here, and copy E to here. It doesn't work. Okay? And it's not uncommon to be off by 1 with the indices. So you really, even for something as simple as this, you usually want a piece of paper and a scratch pad, and a pencil that you can just work out exactly where this loop should start and where it should stop. Okay, so it looks something like this. Add does something like for I equals n minus 1. So we start at position n minus 1. Where do we, not I, let's say j. We start at position n minus 1, and when do we stop? Yeah, so we continue as long as j is bigger than I. Eventually j will get down to I, and that's when we'll stop. Or actually bigger than or equal to I. And each time through the loop, we subtract 1 from I, j, and we repeatedly set a at j plus 1 equal to a at j. Okay. So that'll start at n minus 1. That's here, and copy that to n. And then down to n minus 2, copy that to n minus 1, and so on. Okay? And then, once all that's done, we're free to set a at I equal to x. Anything else we need to do? Yeah?
Well, what about the case where n is equal to a dot length?
That's a very good question. Well, what happens in this case where actually this thing is already full and n equals a dot length? So we better put in some code up here to worry about that, because we can't even do this thing. We can't even do this copying if that's the case. So worry about the case n equals a dot length. That's going to be a problem. Let's say we've worried about that. Then, is there anything else left to do? Yeah?
Increment n.
Yeah. So after we're done this, we've just added an element to this list. So the value of n, which keeps track of the number of elements in the list, should be increased. So we do that. Okay? Now, so that looks good. The only thing we haven't handled is this case where n is equal to the length of the array, in which case we have to do something before any of this happens. And what we'll do is make that someone else's problem by saying if n is equal to the length of the array, then we'll call a function called resize. Okay? I don't know yet how resize works. We'll discuss that soon. We'll leave that for some other programmer to deal with. But let's say that it guarantees the following. After calling resize, we're guaranteed that the length of A is bigger than the value of n. Let's say that's all we really need from resize right now. Yep.
Wouldn't that if have to go inside the for? Because otherwise, if you had one space left in the array, then the for would still run, and then you'd get an error.
No, the for loop only needs one more space in the array. The for loop, the biggest thing it's going to do is, remember it starts at n minus 1, so it's going to want to write to position n, and that means we need an array whose length is at least n plus 1 for that to work. As long as resize can guarantee us that the array length is bigger than n, that's going to be okay. The for loop will be fine. Okay? Yep.
Why can't you just, in the for loop you drew up for add on the left, why can't you just increment n at the start?
Well, I don't want to increment n at the start because then I'll be confused about where this loop should start and so on. I mean, I could do that, but then I have to subtract ones off this thing. Yeah. It's a matter of preference or style. I like putting it at the end because that's when you finally say, this list contains n elements. Yeah. Okay? Good. So that's what resize, or that's not what resize does, but that's how add works. And we can take a look at that. So add works almost like the code I've written on the board. Actually, the loop starts a little bit differently. It starts at n and counts down to 1 bigger than I, but it does the same thing. So first thing is some bounds checking, which we like to do. Make sure they're not trying to insert something at a negative index, and make sure they're not trying to insert something at an index greater than n. The index n is allowed. That corresponds to adding something to the end of the list after all the stuff that's there. And then it's the for loop. And then it's setting a at I equal to x, and then it's adding 1 to n. And right at the beginning there is we check if n plus 1 is bigger than the length of the array, and if so, then we resize. Okay? That's basically the same thing as asking if the length of the array is equal to n. Because we already know that the length of the array is, n is less than or equal to the length of the array. Okay? Any questions there? Fairly simple stuff. Good. Let's think a little bit about these operations and how long they take. So how long does it take us, for example, to get the ith element? That was one line of code. So how is it a function of n? Does it matter how long the array is? How many elements are in it? None of that matters. So this takes constant time, independent of n. And the way we write that is the running time here is O of 1. Any of you seen this big O notation before? Have you ever seen big O of 1 before? So this just says that as a function of n, this running time has nothing to do with n. It's a constant. I'm not going to tell you what that constant is, but it's certainly not related to n. Okay? How about setting this value here? So it's the same thing. It's a one-line array access thing. So this also takes constant time. And again, we just say that's O of 1. Constant independent of n. Okay, how about this add operation? What does it depend on? Yep. Well, it depends on n. Does it depend on anything else? Depends on what resize does. That's true. Anything else? Yep. It depends on the index that you choose. And how does it depend on that? Yep.
If you choose the
Yeah. So if you choose I equals n, then it's basically O of 1. And if you choose I equals 0, then it's O of n. In fact, we can think of this loop here and what it does. How many times does it execute? Yeah. So this loop executes n minus I times. So actually, in terms of the running time of this thing, ignoring resize for now, n minus I is really the parameter of interest. Not n by itself and not I by itself, but the difference between those two things. Okay? And then this takes constant time, and then this takes constant time. So if I'm just worried about this stuff, I'll ignore resize right now because I don't have a choice. I don't even know how resize works yet, so I won't try and tell you how long that takes. Then the way we will write that is we'll say it takes O of 1 plus n minus I time. Okay? N minus I is how many times this loop executes, and this O of 1 captures this, and actually testing the first iteration of the loop or not. You keep the 1 here because otherwise it looks a bit weird if you say O of 0. It's not even clear what that means. Actually, it would have to mean 0. And this function doesn't take 0 time ever, but it takes at least a constant amount of time. Okay? So does anybody want to ask me to clarify anything about this use of O notation? Yep.
So I was under the impression that if you care about what it goes to after the product, the big O notation, and I would think that the constant part of the O of 1 plus n minus I would significantly start to be the n minus I, not the 1.
Yes, as things get bigger, as n minus I gets big, that's the important one variable. It could be incorrect to just write O of n minus I, right? Because if you think of appending to an array, then I is always equal to n. So for that operation, you would be writing O of 0 here. And that doesn't quite feel right. Yeah. Okay. All right. Let's then look at the final operation that we need to implement, which is, well, the final operation that the user is presented with, which is I think we can write that out here. Remove I. So we want to remove the ith element from the list. How do we do that? Yep.
It's really similar to add-I, except you kind of go backwards where you just move, find the ith element, and then you make I plus 1 equal to I, and then I plus 2 equal to I plus 1.
Okay.
So you get to
Yeah. So I would say add I is the one that goes backwards and remove I is the one that goes forwards, but remove I does the opposite of what add I does. And so you do something like, so if I'm removing I, so that's this, the ith element, which is x in this example here, then that's going to create a gap here, which I need to fill in, and I get that by taking element at position I plus 1 and copying it to position I, and then the element at position I plus 2 and copying it to position I plus 1, and then G over F, and then H over G. So that looks something like for J is equal to I, j is smaller than n minus 1, j plus plus, and I'll say a at j rather, is equal to a at j plus 1. Okay? So that implements this thing. Anything else we should do? Yep.
Before running the for loop, we would take the value of I, the value of x hat I, put in a temporary value, and return it at the end of the function.
Yeah, so if you look up the documentation for remove, it's supposed to tell you the value that was removed. So we better do something like, say, I don't know, x is equal to a at I. So we'll save that before we overwrite it. So that implies that somewhere at the end, we're going to return x. Anything else in there? Yep.
We should probably check that n isn't 0.
We'll have some bounds checking to make sure you're not trying to remove something that's not there. So you shouldn't check that. In fact, what we'll need to check is that I is somewhere between 0 and n minus 1. Yep.
N minus minus.
N minus minus. So the size of this thing decreased. Anything else you can think of? Yep.
You may want to resize.
We may want to resize. Yep. Yeah, so if you know a little bit about Java, what you'll know is that keeping this thing hanging around here could be a problem for the garbage collector. So that means that, I mean, these things, in general, these things are objects or references to objects. Now this array is holding 2 references to this object, and really it should only be holding 1. It might be good practice to do that. So you could say that would look like a at n minus 1 is equal to null. So that's erasing that second copy. So just think of what happens, for example, if you do remove n minus 1. Then you're asking it to remove this last element here. And that for loop does nothing in that case. It executes 0 times. And then you would leave, subtract 1 from n, which indicates that that element's no longer part of the list, but it's still sort of hanging there in the list, in the array. And it could be good to clean that up. Okay? And someone else suggested maybe we want to resize. And so here, before we return, we can say something like, think about resizing here. Why would we want to do that? Well, if we made a list that contains 1,000,000 elements, and then we start deleting elements until at some point the list only contains 30 elements, it's still backed up by an array of length 1,000,000. That seems kind of wasteful. Yeah?
Instead of having the j less than n.
So the question is, why don't I make the loop iterate one more time? Any problem with that? Yep. Yeah. If the array is full and you iterate one more time, then you're trying to copy this value onto that value. This value doesn't exist. You'll get a null pointer exception or an index out of bounds exception. Okay. All right. So we can analyze this thing. It's got some lines of code here we can analyze. This takes constant time. This line here takes constant time. This also takes constant time. I don't know what's going to happen with this resizing business, and returning x also takes constant time. So the only question here is about this for loop, which executes how many times? Let's think about it. If I equals n minus 1. It executes how many times? Yeah. Yeah. So this executes something like n minus I minus 1 times. So really the parameter of interest in this thing is n minus I. That's the thing that could get potentially big here. And in total, if we summarize the running time of all of this, we'll give it another O of 1 plus n minus I. So it takes at least constant time, and if n minus I, as n minus I gets big, then so does the running time of that loop. Okay. All right. So this implementation does all of that except for setting the last value to null. This implementation just doesn't bother. That's probably makes it a little bit less than industrial strength. But it actually is, I guess, formally not a bug, but it is a problem for garbage collection. If you're expecting things that you remove from a list to be garbage collected, they may not be in this case. Yep. Yep. You mean if you wanted to remove two values at once? So let's say you had an operation called remove two that removes two values at once. Well, the way I would do it is this loop here. You'd have to adjust the indices. You would have a n minus 2 here, and here you would have a j plus 2. That would do all of the copying that you needed. And then you have to zero out. If you're going to zero them out, null them out, you have to null out the last two values. Yeah. Okay. And there's one thing in this code that's projected up here that's not on the board. We said here we should think about resizing, and this code does think about resizing. And it says the length of A is greater than or equal to 3 times n, then we should resize. So that means that if that's the case, that means that this whole array is only 1/3 full at most. Okay? So that's kind of wasteful. That means 2/3 of the array are just these empty things at the end, and only 1/3 is being used to store list elements. That seems like a reasonable time to do something, maybe make the array a little bit smaller. Okay. Keeping in mind that resize does have to guarantee that the length of the array is bigger than n. So remember, it has to guarantee that, otherwise add is not going to work. So every time you call resize, you need at least space for one more element. So, how would you implement resize? Now we get down to the interesting part. So, what does resize have to guarantee? It has to guarantee that the array A is able to store at least one more element than the number of elements currently in it. Yeah?
Just make a new array of size n, and then just port everything through it, and then destroy the whole array.
Well, of size n is not going to be quite big enough. We need it a little bit bigger, but n plus 1, for example. So I can declare a new array, which is, I will say, I'll just write this out, of length n plus 1. And then I copy everything from A to B. We say B at I gets A at I. So now B has everything that's in A is now in B. And then we just say A equals B. And you all remember the memory model here, that what's really happening here is we have this array that is referred to by a variable called A. We've just created a variable called B and made it refer to a slightly longer array. We copy everything from A into B, and then we say, well, now, in that last line when we say A equals B, all that's doing is saying this variable should refer to this array now. The real work is done when we copy everything.
Would it be more efficient to have some sort of growth factor for it, so instead of just adding one each time?
We'll get to that. Let's see why this doesn't work. Let's start with the simplest thing first. Okay. So this does what we need it to do, right? This guarantees that after I call this thing, there's room for at least one more element in the array A. In fact, there's room for exactly one more element in the array A. So when we're adding, that's good. The array A gets bigger. When we're removing, if the array is only 1/3 full, this means A looks like this. And then we shrink it down just to fit so that it looks like this. Saving a lot of memory, I guess. Okay. So let's test that out. So here's an implementation called slow ArrayStack, in which the resize operation is done exactly that way. So we create a new array whose size is, you can ignore that max, it's just of size n plus 1, because n plus 1 is always going to be bigger than or equal to 1. Copies everything over, and then says A is equal to B. Okay? So, is this going to be efficient? Is this going to be fast?
Well, it's fast. If you're only calling remove, then yeah.
If you're only calling, I would say even, well, first of all, from the operations we've seen, you can't call remove before you call add, so there's never a case where you're only calling remove. But I would say even if somebody gave you a list that's full of elements and you only called remove, then you might run into problems here. Yep.
So if we're just thinking in the vacuum of the add function, this is like pretty inefficient because we're going through like making a whole new array and then iterating through that, and then we're going back to the add function and iterating through it again.
Yeah. Let's think about what happens here if we just do something like this. We create one of these things here, and we just write a for loop where we keep adding to this thing. Okay? So let's see what that picture looks like. Initially, we add the first element, and we have a picture that looks like this. Okay? So we add 0, and we get this array. A has length 1, and 0 goes in there. Now we add another element, and we get a picture like this. Right? First thing we do is we make we have to grow A because it's full. We copy this element into there. Now this is the new A. Maybe I should do it this way. This is the new A, and then we add the new element. Now we add the third element, same situation. This array is already full. So we need to grow it first, copy everything over, change A so that it refers to this array, and then we add the new element. And so on. Okay, so this goes on like this right up until the end, when this process ends with an array of length n. Okay? So that means as we go from here to here, we copy one value, 0. As we go from here to here, we copy two values, 0 and 1. As we go from here to here, we'll be copying 3 values. And right up until the end, when we're copying n minus 1 values. Okay? So if we just, as a rough estimate, we'll count the number of things we copy from one array into another, then that's what we get. Plus 2, plus 3, all the way up to n minus 1. Anybody know what it adds up to? Something like n squared. Does anybody want to hear a story that may or may not be true? Stop me if you've heard it before. So, anybody heard of the mathematician Gauss? Like the greatest mathematician ever? Yeah. So the story goes, when Gauss was 9 years old, and he was in his class, which was probably math and languages and everything else at the time, the teacher got bored or wanted to go smoke a pipe or something, so he gave the students some work to do to keep them busy. He told them to add up all the integers from 1 through 100. And he figured he would have time to go out and smoke his pipe and come back before anybody was done. Didn't help that they were working on little chalk slates that were only this big, and so trying to do lots on those chalk slates is tough. But apparently before he finished writing the question on the board, Gauss told him the answer. 9-year-old Gauss. And he was right, and he did not do it by using, writing this sum down and adding these things together carefully. Instead, he used a very clever trick, which is basically a graphical trick. So we're trying to add up 1 plus 2 plus 3 plus whatever all the way up to 100 or n minus 1. So you think of that as drawing some squares. In the first row, there's 1 square. In the second row, there's 2 squares. In the third row, there's 3 squares. In the fourth row, there's 4 squares. And in general, so we're going up to n minus 1 here. Or let's say we're going to go up to k. And so this goes on and on. This thing here has size k. Okay. The question is, how many squares are in this picture? And the clever thing to do here is to take this picture and turn it 180 degrees and realize that the two pictures that you then have fit nicely together. So if I turn this 180 degrees, then this bottom row ends up here. So we can draw that there. This is k things. this here is k minus 1 things. This is k minus 2 things, k minus 3 things, and so on, and you finish here with 1 here. Okay? Do you agree? Good. Well, how many squares are in this picture? K times k plus 1. So this thing is just a rectangle. It has side length, width, k plus 1, and height, k. So the number of squares in this picture, which is the area of this rectangle, must be k times k plus 1. How many of those squares are yellow? Half of them. So the number of yellow squares, which is the thing we wanted, is k times k plus 1 over 2. Okay. So I think in Gauss's case, that's 50-50, 50-50. In our case, well, our value of k is n minus 1. So this is n times n minus 1 over 2. The interesting thing here, this is n squared minus n over 2. Okay. So if we do this strategy, it's going to take about roughly n squared over 2 operations. So if we add n elements to a list, and the resize implementation that we're using is that, just increasing the size of the array by 1, then it's going to take a while. And well, I mean, let's really see if that's true. So we run this thing. So this is the code that I just showed you. Slow ArrayStack is the implementation that I just showed you that increases the size by 1. And there's 3 implementations before that. ArrayList is from the Java Collections framework. ArrayStack is the one we're working on that does something a bit smarter than what I just described. And Fast ArrayStack is an even more clever one. Okay. So yeah, there you go. It's still going. The slow one is still going. That's trying to add 1 million elements to a list, and it's going to go probably for the rest of the class. So that's certainly not what the Java ArrayStack implementation is doing, or ArrayList implementation is doing, and we can certainly do better because there's something there, some code that I haven't shown you yet that does better. So how do we do better? One of you suggested it already. Add more blank spaces. So like 2 of them? Maybe dependent on the size of your array, or maybe dependent on n. Yeah? Double the size. Okay. Well, double the size of what? Well, remember, resize gets called also when the array gets too empty. So we don't. It sort of goes against what we're trying to do to double the size in that case. But we can double something. Yeah?
Yeah, scale with n, double n.
Yeah. So let's make the array so that it can hold 2n elements. That's what we'll do. Any potential problem cases there? Yep.
If n approaches the maximal representational range integer.
We won't worry about that too much. Yeah. So somewhere around 1 billion, that's going to break down because we run out of things. But that's a problem inherent with Java. Yeah. Either or. Yeah. So when it's empty, n is 0, and we say resize to 2 times n. Well, 2 times 0 is 0, and that's going to break, right? Because try insert into an empty array, call resize to make the array bigger, but it doesn't actually get bigger. So the little edge case there is when n is 0, we still need an array of size 1. And in fact, Java, I don't think will let us allocate even an array of size of length 0. So it'll already throw an exception when we try and create an array of size 0. So that's why there's a math.max there. It's either 2 times n or 1, whichever is bigger. In almost all cases, it's going to be 2 times n. But in that weird case 0, it's 1. OK. So let's write down what we know so far. I'm going to write down a theorem that's going to look a little bit strange. And that theorem says, and the reason I'm writing this down is we're going to see a few things of this type. And then we'll add a special thing here. The cost of calls to resize the following things are true. Get I and set IX run in constant time, and remove I and add IX run in O of 1 plus n minus I time. OK, so you see I just pulled a trick there. I said, ignoring the cost of calls to resize, all of this is true. That's fine. You can do that. But no one is going to be very convinced by this unless you say something about the cost of calls to resize. So there's a second part of this thing. And this is a little bit longish to read. If we start with an empty array stack and do any sequence of m add or remove operations, then the total time spent in calls to resize is O of n. Okay? So this says that the typical thing is you start with an empty array stack because you just create it as a new object. Then you do a whole bunch of operations on it. And if you forget about the cost of the resizing that happens during those operations, this describes the running time of those operations. And more than that, if you add back in the cost of resizing during all that sequence of operations, it's only proportional to the number of operations you did. So we think of that as, on average, the amount of work you do resizing is only a constant per add and remove operation. Okay. So this is what's called amortized analysis. The reason we have to write this in this awkward way is I can't tell you exactly how long an individual remove or add operation happens. Usually, how long it takes, rather. Usually they're fast. Usually all that happens is you move some elements out of the way and you insert X where it's supposed to go, or you remove some elements and that's fine and fast. But occasionally, once in a while, you have to call resize, and that's expensive. And when that happens, the running time of those operations can be huge because you copy the whole array. So instead of looking at one individual operation, rather I'll look at a whole sequence and tell you that all of these resizings that happen during this entire sequence, they don't add up to much more than the length of the sequence. I mean, think of that as, we do this all the time when we do accounting, and the word amortized analysis comes from there. When you get, let's say your cell phone or data plan, you know how much your data plan costs you? $35 a month. Great. You must be in Quebec. You must. Wind, so wind. Me too, yeah. Where it works. And you just told me $35 a month. What if I say, how much does it cost you per day?
$1.12.
$1.12. So how much did it cost you today?
$1.12.
No, how much did it really cost you today? How much did you spend? $0. And then tomorrow, probably $0. The next day, probably $0. But there'll be one day this month when it costs $35, when you actually pay the thing. But still, you can talk about the cost per day just by averaging it over the number of days in a month. And that's all we're doing here. How much is the cost of resizing for one of these operations? In an individual operation, I can't tell you. It might be big, might be small. But over a whole sequence of operations, when we add them all up, we can tell you the average. The average is O of m divided by m, which is just a constant. All right, so let's see how we would prove something like this. So what we're going to do is we're going to look at two consecutive resize operations. So let's say we resize, and after we resize, we have a pretty good picture of what things look like. Our array looks like this. So resize gives you an array that's twice as big as you need. So the array looks like this. It's half full, right? And this half is empty. Okay. So let's say that was, we'll call that then. It's in the past, and it is after last call to resize. Now, let's say we are, at this point in time, we're just about to call resize again. Okay. About to call resize. We'll call that now. So why would we be calling resize? Yep. Yeah. So let's look at the case where we're about to call resize because the array is completely full and we want to add something to it. So that means the picture looks like this. Okay. So that says n is equal to a dot length. So this is the picture when we're about to resize during an add operation. The only reason we do that is because the array is completely full. So n is equal to a dot length. All right. And so what we're about to do here, we're going to do this resize operation. And that thing is going to copy n values. Okay. Now what I'm interested in is, I'm worried that this happens too often. That's when it's going to get expensive. If this happens all the time, then it's going to cost us too much. So I want to know how much time, in quotes, has elapsed. And my measure of time is the number of add and remove operations that I've done in here. So I don't know anything about the exact number. Could have been more or less. But can you tell me any estimates? Can you tell me anything about the number of add and remove operations that happened from then until now? Yeah.
At minimum, there is n.
N? At a minimum, there was enough add operations to fill the array, which means all of these things got, there was enough add operations to fill this thing, and it was only half full before. So what we can say here is at least a dot length over 2 add operations occurred between then and now. There's no way around it, right? That's the only way we get things into our array is by calling add operations. And so we have a dot length over 2 more things than we used to have, so at least that many add operations happened. Do you agree? Okay. And now we're about to copy n values. N is equal to a dot length. So another way of writing this thing is to say at least n over 2 add operations occurred between then and now, where n is measuring the current number of elements in the array, or rather the current number of elements we're about to copy. Okay? So if I'm going to make a resize operation that copies n values because I'm about to add something, then that means the number of things, of add operations since the last time I called resize is at least n over 2. That's good news. Right? So I'm about to pay $30. The number of days since the last time I paid $30 was about 30, so I'm hoping to pay about $1 a day. In fact, 15 days, so I'd be paying $2 a day, but that's the idea. All right, so that's one case. Those are the resize operations that happen because you're trying to add something. The other case is when you're trying to remove something. And this case is similar, but I don't know, for whatever reason, more confusing, slightly more confusing. So the picture then doesn't change. Someone calls resize. The picture always looks like this. The array is half full. Then some operations happen. You remove something. And the array is not, so this is a dot length divided by 2. Now the number of elements in the array is only a dot length divided by 3. Okay? So let's say n is equal to a dot length divided by 3. And you're calling resize. So you're about to copy, you're going to copy n elements here. So what can you tell me about the number of add or remove operations that happen between then and now? Yep.
It was at least n minus square n divided by 2.
Skipping too many steps there. Yes, that's true, but yep.
Should it be a length over 6? Like a length over 6 remove operations?
Yeah, so what's the difference? If you take 1/2 and subtract 1/3, what do you get?
Half a third.
A sixth, yeah. So 1/2 minus 1/3 is a sixth, which means that this stuff here, the stuff that's no longer present, is of size a dot length divided by 6. Now, if n is a dot length divided by 3, that means this is n over 2. So we have, again, at least n over 2 remove operations happened. What does that have to do with what's written here? Let's write down a timeline. On this timeline, on this axis, we will put the operation number. So meaning that we started with this empty array stack. So over here, we have an empty array stack. And then on this timeline, it's punctuated with little, maybe this is an add, maybe this is an add, this is a remove, and so on. That's what these dots are on this timeline, add or remove operations. And the theorem says that there's m of those add and remove operations. Now, sometimes these operations cause a resize to happen. And so, for example, you might have a resize here, which copies this many elements. So you have an array that contains this many elements in it, and you copy these things. Okay? Can I have another resize operation right here? No. So let's call this thing ni. That's the number of elements that were copied in this resize operation. How long before I can How big is this gap before the next resize operation can happen? Yeah. So think of this. This was then. Actually, that's a bad question. I should ask it the other way around. Start with the last resize operation that copied ni elements. How long if I look backwards until the previous one? What's that? Loudly. As loud as you. Well, this is at least, if I'm copying ni elements here, then that means, so if this is now, then the most recent then was back here, at least ni over 2 steps in the past. Agreed? And that's what both of those pictures show you. We have an n here, and then the gap between that and the last one is n over 2. So if this was ni, then this is n over 2. And then there was another resize operation, maybe back here. But this gap is at least, so this is ni minus 1. This gap is at least that. And then there's another one maybe over here, a huge one. But then this gap is bigger, and so on. All the way back to the beginning. So what I'm counting is how much work is done by resize. So I'm counting up how many elements were copied in total by resize. That's the height, adding up all the heights of these stacks that I've made here. Now, how tall can those stacks be in total? Yep. Well, as a function of m, the length of this picture. Well, I know that I can take this stack here and break it in two. So cut it here, and then lay it down flat here, 2 layers deep. Do you agree? I mean, the stack is of height ni. This is of length at least ni over 2, so I could break this thing in two and lay it down flat here. This one I can break in two and lay it down flat here, 2 layers deep. And I can do that with all of them, and none of them overlap each other. So how many blocks are there in this picture then? Yep. At most 2m. Because I can take all of those blocks, reorganize them so that they're laid out on this line, and it's only 2 layers deep anywhere. It's probably less than 2 layers deep in many places, but it's at most 2 layers deep anywhere. So if we write this more specifically, if you don't like this O of m, you can say, during a sequence of m add and remove operations, the total number of elements copied by resize is at most 2m. And that's all resize really does is copy elements. That's the only expensive thing. So that means that the total time spent in resizing is only a constant times m. So O of m. Okay? So it works out perfectly. So now you know why, if you think about this for a while, you will know why you double the size of the array. You'll know why I picked a dot length over 3 to shrink the array. It was to make all of this work out perfectly. If we go back to our experiment here, it's still running. And if you look at our performance of our array stack, the one that I just described, there's how long it takes to insert a million elements, 0.069 seconds. It's actually faster than the one in the Java collections framework. And we can even make that twice as fast still by doing something a little more clever. So already you're at a stage where you can beat the standard data structures in the collections framework.